look at bandwidth control and throttling a task, it is unfortunately a source of latency, because any resource or lock that can be acquired by a task that gets throttled is denied to other tasks until unthrottling this stadium execution and releases the resource. So if you look at generally at this, if you have a task that's scheduled in a CPU-C group with some runtime limitation, once the lock gets throttled, then any other task that tries to acquire it has to wait for the unthrottling to happen. It gets a bit better on preempt-RT because most locks become or have a base involving an RT mutex. So you have inheritance. If the task trying to acquire that lock is, let's say, at least 501, then you boost the throttle to 501. So it skips the throttling until it releases the lock, and then the other task can get it. So bandwidth control and throttling mostly doesn't have an impact on lock acquisition for locks that become an RT mutex. Unfortunately, what we've hit out in the wild is read-write locks, which don't do priority inheritance because they can't sanely do that. And the scenario we have is, again, schedule a task, which does a read on a read-write lock and then gets throttled. We have some other task which does a write lock, so it doesn't acquire it because we only have a reader, but it pushes further readers into slow pass. And then, again, because we're on preempt-RT, a lot of timer expiries are moved from hard RQ to soft RQ context. So in case of RQ, we can end up, again, doing a read lock on lock. We can't really proceed because we're waiting on this other task to successfully do a write, which itself cannot proceed because it's waiting on the lock, which itself can't proceed because it's waiting for the unthrottling to happen. And so you have this circular dependency on preempt-RT at the moment. You could argue that, well, you shouldn't be using this code, which is a fair argument, but unfortunately, we have environments where this is intense and we have to support this. So I've seen that this happens with even Paul. I try to fix the one location because so the problem is if you have a read-write log that can be taken both in process context and software context, you can hit this. So let's try and see, okay, the places where we can take this this log in software context can be punted to some other, what I'll try to do with the even Paul. And when I fix that, I realize, oh, I'm getting errors in other places. So it's actually more of a generic problem with bandwidth control. So maybe we should be doing something else. So there's been a suggestion from Peter, which was, okay, well, instead of sticking with the current approach, which is when we realize that a CFS run queue has run out of runtime, immediately pull the brakes, dequeue the CFS run queue, and then stop the execution of all of the tasks in there. We can give a bit of, let's say, leeway to the tasks and say, let's wait for them to reach a point where they are about to return to user space. So we have some form of guarantee that they're not holding any kernel resource, and then we block them from executing any further. In two approaches to that, which I'm going to talk about. And the idea for me here is to get some feedback on which one is preferable. Do you see other approaches? And both approaches have been sent as RFCs. And okay, yeah, because yes, I tried to look for some conversation on that on the list, but I think it was like offline discussions because I couldn't find any reference. So first approach, the idea is when you realize that a CFS run queue has run out of runtime, you can use the task work mechanism for the tasks so that as they are about to replace, do the throttling. So the tricky thing here, or the different thing with what we have upstream, you can just dequeue the CFS run queue from the hierarchy, and that takes care of all the tasks, because when you go to pick next tasks, they're no longer in the hierarchy, you're not going to pick them. Here, something per task. So instead of saving the CFS run queue in its own state and putting it elsewhere, we have to set CFS run queue dequeue the tasks that are in there, including the tasks that could be in child CFS rankings. So it's a bit more involved. And the unthrottling is a bit tricky as well, because you can end up in situations where the timer fires, we give runtime back to the CFS rank. We want to put the hierarchy back in the same state or the state it was before, but we already have tasks that, for instance, never left the kernel in the meantime. So we are kind of in a limbo state, and we need to like clean it and put it back in something that makes sense. So that's the first approach I went with. The other one that was suggested by Ben Siegel was we actually track kernel tasks and tasks that are executed in kernel space and tasks that are executed in user space differently. So we already have a tree to track the task, right? And the idea is we add one where we treat tasks included in there if they are in the kernel. So by default, when you action a task, you pretty much end up accruing them in both trees. And then when we see that the task is about to return user space, you remove it from the kernel tree. And then when you see that the CFS rank runs at a runtime, instead of, again, removing the CFS rank from the hierarchy, you look at the other tree. So when you're doing picnic task, you're picking kernel tasks. And eventually this kernel only, or in kernel only tree gets empty, and you can do normal throttling when you remove the CFS rank from the hierarchy. So both approaches have pros and cons. The good thing with the first one is the bookkeeping. That's for how many tasks do you have running in CFS rank. It reflects the reality, right? Because we have the task work, task is returning to user space, we remove it from the CFS rank, and we can update the number of tasks in the same manner, which is really good for load balancing, because when we look at the numbers, it's actually what's runnable. The other approach, we're doing kind of a gymnastic with two trees, and I try to implement where we try and keep the counts accurate with what we have runnable, but we're kind of lying because we have trees with a certain amount of tasks, and we're reporting a different number of tasks that's available. So it's easy to, mess this up. In the first approach, most of the overhead is in the throttling and the unthrottling, whereas in the second one, we have some extra overhead at NQ and DQ pass because we are queuing on. Even though it's not too big, it's still there. And the other thing I have in there, yes, when we're doing the DQ in the task work, we are removing the task from the CFS rank queues, and what we like to do is to be able to get to a point where, okay, if you drained the CFS rank queue, you got to put task on there, and then you remove it from the hierarchy as if you were doing normal throttling. Unfortunately, you can do that because if you have a task wake up or a task that migrates from another C group, if then you put it back on this hierarchy and you requeue this, you let all of the other tasks become runnable again, which doesn't work because you want them to be throttable. So you have to, do stuff with the other approach. Throttling and unthrottling stays almost the same. And that's the right audience in the people. The thing I'm not sure what to do is with the throttle clocks. So because for pelts, right, when an entity is throttled and then unthrottled, we want it to look at it as if nothing had happened, like if time had been frozen, or time had been frozen. This works because we have a single point in time where the CFS rank, which is removed and then put back. We have end points where throttling happens because each task is taken out as the throttling was, as the review is. So there's really a single value for the frozen time that we can use. In the implementation I've done, I think I saved the time as the first thing is throttled. The first task is throttled, which means any task that's executing in kernel and then gets back to user space and then move it, this time doesn't get accounted in pelt. So we pretty much don't account the pelt signals, which is lying, but I think is maybe not as bad as saving it at the end and potentially inflating the I'm not sure. I'm looking at you, Vincent, but
So we already have some problem with the throttle task and the because when you're throttling the entity in a group, I mean, you stop increasing the pelt, but then how it reflects in the root in the parent, it's not always as good as it should. So maybe you will make it worse, but it's not perfect already.
Okay.
So
yeah.
Another question is that there you are mentioning the goal is to wait for so not accounting if one thread take any kind of lock. It's just that as long as we are in the kernel space.
Yes, we're using the fact that it's about to return to user space as a heuristic to be we know it's not going to be holding.
Yeah. I was not sure if you were counting only the thread that take whatever the lock and
no, it's any task.
Yeah. For the pelt, there is a problem right now. I would say just now try to not make it worse.
Yeah, okay.
Or maybe fix everything in that will be even better. But we already know that there are some problems in the constituency.
I think that's pretty much all I have. So I see, and then.
Maybe you mentioned this and I missed it, but like, won't this be solved with proxy execution? The lock type is different, or?
No, because even with proxy execution, you will hit the circular dependency. John, do you want to? Yeah, there's that as well. It does, if you look at this one here, for instance, this one, for instance, this scenario is fixed only if P1 is at least CAD FIFO or above. With proxy execution, it fixes it CAD order in a different C group, because then you can borrow the runtime, like the donor context. You have an improvement here with proxy exec, but it's not the problem. I mean, it's parallel to the problem we're talking about, but it's not this issue.
So P0, but with proxy execution, when P1 takes the lock, it won't cause P0 to run, or because proxy execution doesn't?
No, the problem is that you can, so because you have multiple readers potentially, so the write lock can't do anything because we can neither do a priority inheritance on multiple readers, nor can we do multi-bandwidth or inheritance or borrow lend to multiple readers, because you have to keep track of the readers and then find them. That's how Roche asked Stephen. He tried to implement it. It was. Yeah, it worked by some definition of work.
The problem, I guess, as I say, the problem here, this is like the picture up there is basically very simplification. Now, pretend there's 20 readers that writers. The problem is the write lock is dependent on one task. It's dependent, it possibly could be dependent on 20. So it has to wait for 20 tasks before it could continue. And just one of them could have this thing. So actually, I'm not really familiar with the throttle CFS run queue thing. Is that act like a lock then, or is it just?
No, it's just like you could have really anything happens in the meantime, and just eventually this runs. We get time accounted in the scheduler. Oh, we're out of runtime due to like the bandwidth control. the runtime you've given for this C group, and then hold it. But it's just that it happens as the whole locks, and that's even outside of the C, as understand, it's an issue because you added latency.
Yeah, and moving the throttle to the user exit doesn't solve the problem because you still has it as well. But it just moves the post far enough that the kernel is not bothered by it anymore.
It's all like this particular case for us. Yeah. And what you but doesn't solve the user space. But yeah, overall the ask for is the errors are for these. I mean the RFCs, but they can run the test scripts attached with them. I think I'm leaning back towards going back to the first approach and developing that. But yeah, feedback on these.
Yeah, I think my preference goes to one as well, but I must admit I've not actually seen the patches for the dual tree due to circumstance.
I mean, I can resend both of them based on something recent and for them for people to test.
But my mail backlog is amazing.
So yeah, if no other questions or comments, can get some time back on paper.
Maybe can you tell me what problem here because
God, I love Pelt. So normally, if you throttle the CFS run queue, what you do now is you take the CFS run queue out of the hierarchy. Like you save time in the Pelt fields, so that then later on, when you unthrottle, you can see, oh, we were throttled for this amount of time. Discard that from the Pelt clock, so that it looks like a continuous thing. Like the throttling never happens. Like the task for the task in the run queue for that CFS run queue, it's as if nothing had happened. So if at T0 you get throttled, T1 you get unthrottled, there was no difference to Pelt. It's like we skipped time. Here it's a bit more difficult because we don't throttle everything at once. We throttle, like we wait for the task to reach the user space and then we DQ them. So they have to be running, then we DQ them one by one. So there is no single point in time where we can save this snapshot to then deduct it from the Pelt clock later.
the relationship between, I mean, the task or the shared entity for the task group is part of another shared entity for a group or for a task group, right? How do you handle this? The contribution of the task or the task group is part of another one, but this other one is not throttled. So
just as normal, like as long as that's normal. Okay, because normally again you just remove the CFS rank from the hierarchy and it stops. I mean, the tasks aren't runnable, and you remove. Do you remove the load? I think you do. Yeah, you remove the load from the parents as you throttle. The load and the. No, we leave it on.
No, we leave it on because we don't only do it in detach, attach, and attach.
So actually, that means that there's another problem because we actually DQ the task.
I just wanted to clarify.
Well, thank you for the comment, because that's an extra thing to think of.
Q and NQ, we don't do anything.
Yes.
This where we go. I think we came across this issue already like 5 years ago.
Yeah, when we were looking at bandwidth.
Yeah, I just want to make sure.
Yeah. Thank you.
Problems.
So if you were ever to do a flattened run queue for the alternative C group implementation, you'd hit this problem as well, because then you cannot simply DQ a C group entity, because the C group entities won't be there.
Right. Is this back on the menu, by the way, or?
Well,
maybe.
So the Facebook people initially presented this as a reason for the whole BPF drama thing. Like they cannot use C group scheduler as we have it because too much overhead, so they have to do their own thing. I'd like to get that off the table. I mean, C group scheduling is expensive. I mean, there's no ifs or buts about it. So if we can fix that, everybody gets an improvement. But yeah, it needs to be solid enough. I mean, the last time Rick tried it, there were some issues identified by Paul Turner. Specifically, herd wake-ups, or thundering herd wake-ups, they'll skew the fairness of the but yeah, there's lots of threads on that. I think the variant that TJ implemented in his actually suffers from that problem as well. It's just not something they seem to care about.
Regarding the C group, what is taking that much time is the fact that we are looping over the hierarchy. So we are.
Yeah, it's the hierarchical iteration. I mean, for every schedule, more or less, we iterate the C group hierarchy up and down, and that's just a lot of cache meshes and memory traversal and compression. Yeah, it hurts.
Okay.
Maybe
Do we check? We have some recent change which happened with this task group load shared across all the CPU, and we have some patch which have been merged where we are limiting the access to that. Did they do some more tests? Not because it seemed that this TG total load was one main bottleneck and root reason of the overhead of using C group. I would be curious to see if that this overhead is that much now.
Yes, the thing was specific was very painful on NUMA machines, I think. But I think Facebook mostly runs single or at most dual node machines. But I have no idea when they tested this last.
Yeah. Okay. It might be worse for them to make a new test with this latest improvement. And I think we did also, there was some EES also general variable which were accessed from time to time. Only some read, but we have a skip. Yes, we have skipped a lot of global variable access recently.
Yeah, but I mean, you can easily test it and make a C group hierarchy that is 7 or 8 deep, and run something that schedules a lot, and then profile the thing. You'll see it being very expensive. And deep C group hierarchy seem to be all the rage. I mean, I think it's silly, but who am I?
Yes, dumb question, but going to the actual issue that you presented. Since you mentioned you saw this in a few cases, I'm wondering, given the pain of actually fixing this, might be worthwhile to look at maybe rewriting those.
This one I started with trying to fix the individual thing, and then when I fixed that, I started getting other ones. I was like, that's actually. It's quite as much as we try to like remove with white logs and replace it, there is still usage unfortunately. And from what I understood, there was like an interest in doing this just from latency perspective, not even preempt RT. I mean, this is like, okay, we fixed the bug we have with preempt RT, but we also get latency improvements for other use cases.
Right. I mean, Android has this background group like we've seen this morning. And I think they've experimented with bandwidth limits on that as well. But if a very low priority group gets throttled in that holden resource or kernel resource, you're up a tree. The whole system comes crashing down. And very bad for the latency.
Okay, we're done.
Yeah.
Okay, thank you.
Yeah, thank you.